When you were talking about magnetic fields, remember it was mentioned to you that magnetic field can be represented in the form of field lines. So if I have a bar magnet, I can represent the field around the bar magnet in this manner, right? In a manner similar to this. Then after that, it was also mentioned to you that spacing of field lines, it was mentioned to you that when you're talking about field lines itself, spacing of field lines is a measure of field strength. So what was mentioned to you then was that the closer the lines, are to each other, or rather just the closer the lines, the stronger the field, vice versa lah. So the idea was that you can represent a magnetic field using field lines, and the spacing of the field lines will actually be a measure of your field strength. Now, when you're talking about the field lines, the magnetic field lines, they can also be known as magnetic flux lines. Okay, the field lines here for magnetic field, we normally tend to refer them as magnetic flux. Okay, so think of magnetic flux as just the magnetic field lines. Okay, now if you talk about, say, a particular area, maybe I have an area like this, and then I tell you that there are like 3 flux lines going through it, and then I'll say that I have the same given area, but this time I have a lot more flux lines going through it, maybe this much, like this. I would say that this one has a higher flux density than this one. This one has a higher magnetic field strength than this one, right? So this one, I would say this one is stronger magnetic field. This one, I would say it has weaker magnetic field. If I were just to look at a given area and I see the number of flux that passes through it, here I would say that this one has stronger magnetic field, this one has weaker magnetic field. The reasoning is because you see here, for that same given area, you notice that the spacing between the lines for this one is a lot smaller compared to this. So as you recall, I told you that the spacing of the field lines or spacing of the flux line is a measure of the field strength. The closer they are to each other, the stronger the field. Looking at it another way, if say you have a given area, and then you see that in that given area there are a lot more flux lines, that one must be a stronger magnetic field, because it implies to you that the lines are more close to each other. Okay, so the concept of magnetic field strength here, I told you in your A2, we don't normally call it as magnetic field strength, right? We call it as magnetic flux line or magnetic flux density. So here, for your case here, your magnetic field strength that time I mentioned to you. Oh, okay, yeah, no problem. Right, so yeah, so for your magnetic field strength, we can say that it is actually also written as magnetic flux density. I mean, we can also say that it is magnetic flux density. So that time I mentioned to you that when you're talking about magnetic field strength, we normally don't use the term magnetic field strength. We call it as magnetic flux density. That was the formal term that you use. So that magnetic flux density that we're using to represent magnetic field strength is actually talking about this. When we talk about density, it's talking about how much you can find something in a given something, right? Like in the concept of density you learn in AS is the amount of mass that you can find in a given volume. So the magnetic flux density here actually refers to the amount of magnetic flux you can find in a given area. That one, the amount of magnetic flux you can find in a given area, represents your magnetic field strength, how strong it is. So thinking about how it is defined, you can say the magnetic flux density is actually something like this. B is equals to flux over area, where flux is your magnetic field lines, area is this area that you have here, and B is your flux density. Okay, now this one here is your magnetic flux density. The magnetic flux density here, you don't use this to define your magnetic flux density. You remember in your previous chapter, I told you magnetic field, magnetic force acting on a wire is BIL, and then B is magnetic force over IL. Your magnetic flux density is defined from this: force per unit area per, force per unit current per unit length. You use this to define your B. But for your case here, B also being flux over area, you do not use this as the formal definition of flux density. Instead, you use this as the formal definition of your flux. Okay, the symbol phi here represents flux. Okay, so the magnetic flux is actually the product of magnetic flux density B and the area A when the flux is at right angles to the area. So that is what magnetic flux is. And magnetic flux has a specific unit that's associated with it. That one is Weber. Okay, if you're talking about magnetic field strength or magnetic flux density, the unit is Tesla. If you're talking about magnetic flux, the unit is Weber. All right, so 1 Weber is actually the magnetic field, magnetic flux. If a magnetic field or flux density 1 Tesla exists at right angles to an area of 1 meter squared. That's what magnetic flux actually is. 1 Weber actually is. Okay. Now then, after further to that, you need to talk about the concept of flux linkage. Now, what is flux linkage? Flux linkage is just simply the number of fluxes through all the coils of a wire. Okay, if say you have a coil with many turns, your flux linkage is just simply the number of flux through each turn in that coil. It will be a better idea to draw this to just tell you what it means. If you have, say, flux linkage is normally used for coils with many turns, all right? So let me just illustrate to you what is flux linkage first. You have one, if I have something like this. Okay, say you have a coil with 1 turn, you have a coil with 3 turns, and you have a coil with 5 turns. And then now I tell you you have magnetic flux. Say 3 magnetic flux that goes like this. Now here, your magnetic flux is considered to be 3. Here also is 3. Here is also considered to be 3. But when you're talking about flux linkage is actually number of turn of coils multiplied by the flux. So this one would be just 3. This one would be 3 times 3. This one would be 5 times 3. This is what flux linkage is. That's why it's, when you want to think of it, what actually is flux linkage, it's actually just you adding up the flux in each coil, sorry, in each turn of the coil together. That's all. All right, that's why it's N phi here. And also because you know that phi flux is actually BA, flux linkage is actually NBA. Okay. Now this is the proper definition for it. This is the proper equation for it. Don't go and cancel out the N and N. You're only going to get back phi equals to BA here. All right. So this is what flux linkage actually is. All right. So if nothing else here, then this one should be okay. Now then after that, let me just clear all the drawing. Okay, so I'll clear this one off. Okay, right. For your EM induction part here, a lot of the things here is just very descriptive. It's just in concept. I think it's better to do some questions, but let me just run briefly through this for you. Now, you know that if you have a magnet and conductor, you tend to be able to generate electricity. You can generate current or voltage out of it, right? In some cases. So how do you go and generate current or voltage or electricity out of it? There are a few ways in which you can do that. You are using a process called electromagnetic induction. What you normally just need is a magnetic field and a conductor. So some of the prominent examples you would have is, say you have a motor and then you have a voltmeter. So for the case where you have a motor and a voltmeter, you know that most of the time if you have a motor, you connect it to a power supply. You connect it to a power supply and you switch on the power supply, the motor will start to turn, right? But what if this time you don't connect your motor to your power supply, instead you connect it to a voltmeter, and then this time you manually turn the motor? You will notice that as you manually turn the motor, you're going to cause the voltmeter to deflect, indicating there's the presence of voltage generated. The faster you turn your motor, the higher the magnitude of the voltage. And then you'll notice that if you switch the direction of your turning, the voltmeter seems to be deflected in the opposite direction. This is one observation here if you're talking about a motor. Another two examples would be, say, if you have a coil of wires, you have a magnet, that coil is connected to an ammeter. For the magnet that you have, you push the magnet in and out, and then you see that you have a current generated through the coil. So the observations you see here is that the faster you go in and out, the bigger the deflection of your ammeter. And you notice that if you push in the coil, your ammeter deflects one side. You push out the coil, the ammeter deflects the other side. Okay, so there's something that you can see for the magnitude and direction here. You want the magnitude to be larger, you just make it faster. Push in and out faster. You want to change the direction, you change the direction in which you're moving the magnet. Okay, then if you have a case where you have a wire now connected to an ammeter and you place it in between two bar magnets, you move your magnet up and down, you're going to cause a current to be generated also. And then the observation here is also a bit the same like the ones before this. If you move your wire up, the ammeter deflects one direction. If you move your ammeter down, the wire deflects another direction. And then after that, the faster you move in and out, the bigger the magnitude of your deflection. So this one here is showing to you that somehow or another, when you have a conductor and you have a magnetic field, and then you see that there's some motion between them, somehow you're going to generate electricity, voltage, or current. So that one is electromagnetic induction. How does it actually work? I will base this on the example of your third example here, where you have a bar magnet and your wire. Now, you will know that your bar magnet has magnetic field, and the magnetic field is represented by field lines called magnetic flux. If you have a conductor, and then your conductor is moving in and out of the magnetic field, what you're actually doing is that you're cutting the magnetic flux, okay? Right, so you cut the magnetic flux, you're going to generate a current, you're going to generate a voltage. So the thing here is that if you want to generate electricity in the form of current or voltages, you need to have flux cutting, okay? You need to have a magnetic field, you need to have a conductor, and there must be flux cutting for electricity to be generated. Okay, that is one way in which you can get flux cutting. As there is one way in which you can get generated electricity. Another way in which you can also get electricity in the form of voltages or current is if you have flux linkage, change in flux linkage. You consider the case for this one as similar to the second example here. Now, just now my magnet was not anywhere near the coil, right? So when my magnet was not anywhere near the coil, there is no flux linkage through the coil. But then once I place the magnet near the coil, like in the case where I try to move it in, you will see that there is now magnetic flux linkage. So there's a change in magnetic flux linkage here, which in turn causes induced current, induced voltage. Okay, so here I have a case where I change in flux linkage, so I have electricity generated. For this one, I have flux cutting, so I have generated electricity also. Okay, so in terms of talking about the electricity that you generate in terms of voltage, in terms of current, there are two laws that you need to know. These are the two main laws that you need to know. The first law is Faraday's law. Faraday's law talks to you about the magnitude of your EMF generated. So here it states that the magnitude of induced EMF is directly proportional to the rate of change of flux cutting or rate of change of flux linkage. As I mentioned to you, if you want to generate electricity, you have to cut the flux or you have to change the flux linkage. So the rate of change of those is what causes you to have your EMF, and the magnitude depends on it. Okay, so for Faraday's law itself, it is very specific. It's only for EMF. If you were to change it to induced current, it will be marked as wrong because Faraday's law itself states for EMF voltage, not current. Current and voltage are two different quantities, so you cannot mix them up. Okay, so don't put induced current. So expressed mathematically, EMF is rate of change of flux linkage, rate of change of flux. If you want to write it out in the form of an equation, this one is how it looks like. Okay, EMF is rate of change of flux. Yeah, there's something I think I should kind of answer here. Now, when you say rate of change of flux linkage or rate of change of flux cutting, this one is already considered as rate of change of flux. Sometimes you may see the term rate of change of flux linkage. Sometimes you may see the term rate of change of flux cutting, or sometimes you may see the term rate of change of flux. They all mean the same thing. Okay, so they mean the same thing. So in my case here, EMF is rate of change of flux, delta phi over delta t. The negative there is just something to indicate to you the presence of Lenz's law, which tells you that the induced EMF is always such as to oppose the flux change that causes it. You don't need to bother so much about the significance of the negative. We won't test you on that. It's there because of Lenz's law, that's all. All you just need to know is that if you want to find the magnitude of EMF, it is equal to the rate of change of flux. Okay? This one is rate of change of flux. This one is a general form of the equation. Now, if you have a coil of wires with N turns, this can be modified to become this. Your EMF is actually rate of change of flux linkage. Okay, you're only changing flux to flux linkage now by adding an N here. It's still the same form. Okay, so Faraday's law tells you about magnitude. That's all. If you want to talk about the direction of your induced current or direction of your induced EMS, or specifically the direction of your induced current, your Lenz's law will tell you that. Lenz's law will tell you the direction of induced current. Okay? They tell you that the direction of induced current is always such as to oppose the flux change that causes it. So this one will tell you the direction of your induced current. What do we actually mean by that? It will be easier to look at it this way. Your Lenz's law is actually a consequence of principle of conservation of energy, which tells you that energy cannot be created, but it must be converted from other existing forms of energy. So the easiest way I can just tell you is this one. If say I have a coil and I have a magnet, you know just now from the previous example, if I were to push it in, I would have EMF induced, I would have induced current, right? Because like here, before I put it in, I do not have flux linkage in the coil. But once I put it in, now I have flux linkage in the coil. I actually have change in flux linkage over a given time. There's rate of change of flux linkage. So there's going to be EMF, there's going to be current. But the question is, where would the current actually be flowing? You see, for a coil, your current can actually flow this way, or it can actually flow this way. But how do I know which one is actually the correct direction? Here we will tell you this direction is not correct, but this direction is correct. But why is it specifically so? If you remember your right hand grip rule, which is this one here, where we tell you that the thumb represents your magnetic field direction, the curl or your finger represents current. This is right hand grip rule. For the case of a solenoid, right now I want to see the direction of the magnetic field produced by these two given in this current direction. If I have a case where my current is flowing like this, my eye is like this, my eye induced is flowing like this, you will see that the direction of your magnetic field is like this. Okay, so this part will be your north pole, this part will be your south pole, because here you know that your magnetic field that you produce will be something like this with this given direction here. So the lines coming out here is north pole, the lines going in here is your south pole. So now what does this tell you then? You see, when your induced current flows like this, you're going to have a magnetic field that is produced with this polarity. Now, this polarity here is north here and south here. When you look at these two polarity here, this is north, this is south. What this means is that the moment you have induced current and you generate a magnetic field here, that magnetic field is going to pull your magnet in even further. It's going to cause you to have an even larger flux linkage, or it's going to cause your magnet to cut even more flux. So it's going to cause your core to cut even more magnetic flux. So the thing here is that you see, if you have a magnetic field with S pole here and N pole here, this part is attractive. It's going to pull the magnet in even further, even faster. You're going to have larger flux linkage change. You're going to cut even more magnetic flux. You're going to cause even more EMF. You're going to cause even more induced current. So you're going to get even more electricity. So it seems like you don't really need to do anything here. It's just that as long as you you give it a little nudge where you produce the magnetic field will take care of everything by itself. You will suddenly get free electricity. So this one doesn't seem to be correct, because this one is telling you that your energy seemingly came from nothing. You don't need to do anything. It will just generate electricity by itself. The magnet will just pull the coil here will just pull the magnet in and then cause more electricity to be generated. So this one is wrong. It's not following principle of conservation of energy. But what if you consider a case where your direction of induced current is opposite? This is the direction of your induced current. So you see here, the direction of your induced current, if it flows like this, you use your right hand grip rule, your magnetic field direction is here. So your magnetic field that you get, this one will be your north pole, this one will be your south pole. Now when you then look at the interaction between these two ends here, this one is repulsive. So if these two ends are repulsive, that will mean that if you want to push your magnet in even further to get even more flux linkage, to get even more flux cutting, you actually have to overcome this repulsive force. You actually have to do work to push it in. So here, the work that you actually do is actually being converted into the electrical energy that will be generated in your core later on. So this one follows conservation of energy, which tells you that energy must come from something. In the case here, your electrical energy in your core actually came from the work that you do to push the magnet in. Now this one seems more logical according to the principle of conservation of energy. So the actual case that will actually happen in real life is actually this, as a consequence of Lenz's law, which tells you that your induced current will always be in such a way to oppose the flux change that causes it. Okay, another way to look at this one here is this. You see, if I were to have the magnet here like this, sorry, let me just wipe some things off here. If you to look at this case here, my magnet coming in it is the flux linkage increase that causes EMF, right? Moving from here to here is the flux linkage increase that causes EMF. Lenz's law will oppose that flux linkage increase if you view it this way. How this EMF is caused is because there's an increase in flux linkage. So Lenz's law will tell you you will try to oppose that. You will try to flow in such a way that it won't cause the flux linkage to increase any further. So this one here, if you want to look at Lenz's law in another way, you remember this statement here, whatever caused the EMF change, it will try to oppose it. So if here your EMF increase, you get EMF because flux linkage increase, your Lenz's law will tell you that it will try to oppose this. It will prevent your flux linkage from increasing. So in that sense, when you look at these two examples here, where I tell you that this one here was attractive, and then this one here was repulsive, which one here is actually trying to oppose the flux linkage increase? This one here is not opposing it, right? This one is causing it even further, right? It's causing the flux linkage to increase even further, right? Because this is trying to suck the magnet in. So this one is not causing the flux linkage increase to lessen. It's not opposing it. So this one is wrong. But this one you can clearly see that they're being repulsive. It is trying to prevent the flux linkage from increasing even further. So this one is correct. So you can view it in this way also as to why my current flows in this direction rather than this. Okay, so that is Lenz's law, right? So that other thing here could be this. Then after that, I just go through one last example here for you, your Lenz's law again. Then after that, we'll just do the examples. So same thing here again, you have a magnet, you have a wire, okay? We tell you that your wire, you're pushing it down. So when you're pushing your wire down, you're cutting the magnetic flux, you're causing induced current. But the question is, where would be the direction of your induced current? Will it be flowing in this direction? Or would it be flowing in this direction? Okay. The wrong one is this one. The correct one is this. But how do you know? So say for example, right now, when you go and push your magnet, your wire down, you have induced current flowing in this direction. You can try to predict what is the magnetic force that is produced inside your wire. Okay. What do I mean by that is, you remember your Fleming's left hand rule, which tells you this is magnetic force, this is flux, magnetic field, this is current. So now you have magnetic field, you have current. This one by right should generate a magnetic force. What's the direction of your magnetic force? Here to here, here to here is your B, here to here is your current. If you use your Fleming's left hand rule, you see that your magnetic force is downwards. Okay, so your magnetic force is downwards here. Notice that if this is the direction of magnetic force, that means this part you don't need to push anymore. You just need to give it a small nudge. You start to have current, you start to have a magnetic force. The magnetic force will take care of itself. It will push your wire down even further. It will cause you to cut more flux. You will start to have even more induced current, induced EMF, more electricity, seemingly out of nothing. So this one again is not correct. But if say you have induced current in this way, where your magnetic field is this way, B, your I is this way, you will see that your magnetic force is here. So this one is trying to oppose the force that you originally pushed down. So if you want to push down even more to generate more flux cutting, and hence more electricity, you actually need to do work to overcome this force. So the work that you do is actually converted into the electricity that you generate here. Okay, so this one is sensible according to principle of conservation of energy. Okay, so that one is okay. If you want to look at it another way also, according to Lenz's law, you are trying to oppose the flux change that cause the induced EMF or induced current. If you go from here to here, you are cutting more flux. Your flux cutting is increased. That cause the EMF. Okay, so Lenz's law will tell you you will try to flow in such a way to oppose the flux change that causes it. In this case, the flux change is increase in flux cutting. So whatever current that flows will be in such a way to oppose this to oppose this flux cutting increase. It will try to prevent more flux from being cut. So you see that your current flows in this way such that you have a magnetic force this way, you're actually causing more flux to be cut. So this one is not following Lenz's law. But you see that the current is flowing this way such that your magnetic force is this way, is actually trying to prevent more flux from being cut. So this one should be correct according to Lenz's law. Okay, so this is in general how Lenz's law works.